Welcome to The Explainer. For anyone who wants to become a scientist or an engineer, there are certain rites of passage, and one of them is definitely Chapter 4 of Marsden and Trumba's vector calculus. This is the moment where the equations stop being just symbols on a page and, well, they really start to describe the world we all live in.
Just listen to that quote for a second. One of the great breakthrough ideas in the history of human thought. That is a huge claim, but you know what? It's absolutely true. This concept of a field is like the secret ingredient that allows us to mathematically describe, well, pretty much everything, from the pull of gravity on a planet all the way to the flow of air over a jet's wing. And the journey to really get it, it starts right here.
So where do we even begin? Let's zoom out and start with a really fundamental question. How do we take the pure, abstract language of math and use it to describe the messy, moving, dynamic world that's all around us?
And that's really the core challenge, isn't it? Our universe isn't a static photograph. It's a movie, and it's always in motion. So to capture that, we need a special kind of mathematical language, one that's actually built for change and for movement. And that language is vector calculus.
Honestly, you can think of this chapter as a kind of Rosetta Stone. Seriously, on one side, you've got the abstract world of pure math, derivatives, vectors, all that good stuff. On the other side, you've got the physical world of mechanics, electromagnetism, and fluid dynamics. This chapter is the key. It's the translator between them. It gives you the toolkit that every single physicist and engineer absolutely needs.
All right, let's start actually building that bridge. Marsden and Trumba begin with a really beautiful, simple idea. They say, look, if we want to describe the universe, let's start small. Let's just figure out how to describe the motion of one single object moving through space.
And the tool they use for this is called a vector-valued function. It's an incredibly elegant idea, really. You give the function a time, t, and the function, let's call it c of t, gives you back a vector that tells you the object's exact x, y, and z coordinates. It's like having a perfect, continuous GPS log for an object's entire journey.
Now here's where the magic of calculus really comes into play. If you have that function for the path, you can find the velocity at any instant just by taking its first derivative. And what if you want the acceleration? Well, you just take the derivative again. It's that simple. With just one function, we can get a complete breakdown of how that object is moving.
And this is the punchline. That purely mathematical thing, the second derivative, f double prime of t. It isn't just a number. It is acceleration. And through Newton's famous F equals ma, it connects directly to the physical concept of force. All of a sudden, our abstract calculus isn't just describing motion anymore, it's describing the very forces that cause the motion in the first place.
And it doesn't even stop there. By integrating the speed, which is just the magnitude or length of our velocity vector, we can do something incredibly useful. We can calculate the exact distance the particle has traveled along its path, no matter how much it twists and turns. This is called the arc length.
Okay, so we've pretty much mastered how to describe a single particle moving. That's a huge step. But, the real world is a lot more complex than that. What if we want to describe the forces that are acting everywhere in a region of space, all at the same time? Well, to do that, we're going to need a new tool, the vector field.
And this is that big breakthrough idea from the opening quote. Instead of just tracking one little particle, I want you to imagine filling an entire region of space with tiny arrows. At every single point, there's an arrow, a vector, that tells you the magnitude and the direction of something right at that location. And that something could be the force of gravity, the velocity of the wind, the strength of a magnetic field. We've just leveled up from describing a single path to describing an entire space. And once you know what you're looking for, you start seeing vector fields everywhere. A weather map that shows wind patterns, that's a vector field. The invisible pull of Earth's gravity, that's a vector field. The flow of water in a river, faster in the middle and slower near the banks, you guessed it, it's a vector field. This concept gives us an amazing way to visualize and analyze all the unseen forces and flows that are constantly shaping our world.
So, now we can visualize these fields. But how do we analyze them? How can we describe what's happening at just one single point inside, say, a rushing river or a swirling storm? For that, we need two new mathematical tools, divergence and curl.
These are two fundamental operations that tell us about the local behavior of a vector field. In really simple terms, divergence measures how much a field is spreading out from a point, while curl measures how much it's rotating or swirling around a point.
Let's make this more concrete. For divergence, imagine the surface of a pond. A point where water is bubbling up and flowing outward, like from a little fountain, has positive divergence. We call that a source.
A point where water is flowing inward and going down a drain has negative divergence. We call that a sink. It's basically a measure of how much stuff is being created or destroyed at a single point.
Now for curl. Imagine placing a tiny little paddle wheel anywhere in that water. If the currents around it cause that wheel to start spinning, then the vector field has curl right at that point. The faster it spins, the bigger the magnitude of the curl is. And what's really cool is that the curl is also a vector, and its direction tells you the axis of rotation, kind of like pointing your thumb up while curling your fingers.
So we have these really powerful tools for analyzing vector fields. But this is where things get super interesting. Because these concepts, they aren't just for solving textbook problems. They are a gateway to some of the most profound and deep ideas in all of physics. Deep in the supplementary material of the book, you can find this really intriguing diagram. It shows two possible paths an object could take between 2 points in time. And it turns out nature has a preference. It doesn't just choose any old path, it always chooses the one specific path that minimizes a quantity called action. This is the true path, and the whole idea is known as the principle of least action.
And let me be clear, this is not just some mathematical curiosity. The principle of least action is a staggeringly deep and fundamental law of how the universe works. It's a more elegant and powerful way of thinking about the laws of motion, and it's a cornerstone for both quantum mechanics and general relativity. All those tools we've been discussing in this chapter, they are the very first steps on the road to understanding this profound principle.
So let's bring it all together. What we've really seen is that learning about vector fields, divergence, and curl isn't just about mastering a set of computational tools. It's about learning the fundamental grammar of reality itself. It's about uncovering the deep symmetries and conservation laws that are woven into the very fabric of our universe.
And that's the real power that's packed into this one chapter. It gives us the language to describe motion, to visualize invisible forces, and to get our very first glimpse of the deep operating principles of the cosmos. It's like the key that unlocks the book of nature. The only question is, what other secrets are just waiting to be read?